Alright, scalars and vectors. Pretty okay topic. Scalars are quantities which only have a magnitude. Some of you guys, I know I hate the word as well. Magnitude just means amount. Yeah, so let me write this for you guys. Magnitude is the amount, like a number to them. So obviously speed, you can't just say I have a speed. You have to say like 40 miles per hour or 50 miles per hour or 80 miles. You give like some context, right? So that's the magnitude. But if you say 40 miles per hour east, you have a number and a direction. So that will now turn into a vector. So what we need to understand is scalars do not have any direction, any sense of direction. Vectors have a sense of direction and also, number to them. So they both have numbers, but this has the added bonus of having a direction. For example, give you a very good example. Forces are what? Vectors or scalars? They are obviously vectors because forces always have arrows, which imply they have a direction, and they also have a number to them. So force is a vector. Stuff like mass, it's just how heavy someone is. That's just in kg, so that's just a scalar. You're not applying your mass anywhere. But weight is a force as well. So you just have to memorize them. Speed is a scalar. So speed is me just saying I'm going 40 miles per hour. Velocity is me saying I'm going to 40 miles per hour north or northeast. Temperature, we know, doesn't have any certain direction. It's just everywhere, pretty much. Time has no direction. Energy has no direction. Force, definitely. And I think this, you do not memorize this. It's just, it should make sense due to how many force diagrams we've done. Arrows, so they definitely are a vector. Acceleration, obviously, if your forward force is more than your backward force, so in a car, if your engine force is more than your air resistance, you move faster. But if your air resistance is more than your driving force, you decelerate, you slow down. So acceleration is also a vector. Velocity is just speed with the added bonus of having direction. Displacement is distance with the added bonus of having direction as well. So make sure you guys memorize these, yeah? And understand this as well. So once again, magnitude is just amount. Next thing is distance time graphs. Some of you all are going to hate this, but oh well. The only two things they can ask you is either you label different parts of the graph or calculate the speed from the graph. Distance time graph, please, and I stress this, time is always on the x-axis. The x-axis is reserved for the thing which always or does not get affected by anything else. Time affects us, affects how things work. Nothing affects time. Time does not care about anything, anyone, so therefore it calls the shots and it's down here. The person who gets affected by whoever calls the shots ends up here. So we know that as your time increases, your distance might either go further or decrease, yeah? So distance always there, time is there. Just in case I ask you to plot. Now, what we need to understand is, on a distance time graph, and you have to come to terms with this, you can't just memorize this. Distance is equal to what? Speed times time from key stage 3. So rearranging this, speed is what? Distance over time. And I'm sorry, you just have to use some maths here. So let's do this. Shout out to Mr. Deco. So you got a constant gradient there. All we're trying to say is constant gradient just means that you have a linear line, aka is a nice straight line upwards or downwards, doesn't really matter, but you have a line like that. And that means is this graph shows that you have distance on here divided by time. So if you look there as well, distance divided by time is speed. So all we can say is if your gradient is constant, your speed is also constant, right? So whenever you have a line like this for a distance time graph, just all you guys do is you look at the graph, this divided by that, what does that give you in real life? Speed. So that means speed is constant. Here, your distance is the same. So if let's imagine you had like a number 20 there, you're staying at 20 meters for all this time. So you're not moving. So that means, what can you say? You're either stationary. Yeah, that just means you're stationary. You're not moving. Yeah. So because obviously your distance remains the same. Here, your distance is increasing again. So obviously you're moving. So there is some speed. But if you guys think about it, you're getting less and less and less and less steep. So that means you are actually accelerating. Or actually, you know what? Let's not even talk about that. I don't think that's very accurate. Just say that speed is changing for now. Yeah, so yeah, ignore accelerating. So once again, constant speed looks like this. Changing speeds when you have a non-straight line, like a curved line. But here we have another straight line. So what we can say is constant speed again. And if they ask you to describe the motion here is you're traveling at a constant speed back to where you started from. Because remember, the bottom is your distance 0. So I left my house. I can give you let me give you guys a story to it. I leave my house at a constant speed. I stop at the petrol station for a while to buy some food. Then I start jogging. And there I stop again because I'm so unfit. So I just, pant and huff and puff for a while. Then I decide, you know what, let me run back home. So I run back home at constant speed and I reach my house there. There you go. So when you touch base here, you reach the point where you started from in the very beginning. Yeah. So once again, I've labeled the different parts for there, and I've told you how to calculate speed by basically, if you have to actually use numbers, let's imagine this is 20, this is 0, and the time there is maybe 5 seconds, right? So if you want to find the speed here, because it's the same throughout, you do your change in distance. So you start 0 meters, you went to what? 20, right? So I do change in distance, which is 20 minus 0, divided by change in time. My time in the beginning was 0. I went to 5 seconds. So I just do 5 minus 0. So it's 20 divided by 5, which gives you 4 meters per second. Let's do another example. I will not show you how to find the speed of curved lines yet. That might be a bit hard. But if you guys want help, you can also email me individually. 6 seconds there. So if you want the speed there, and you start with 0. So my change in my distance is what? 30. So I do 30. My change in time is 6. So my answer is 5 meters per second. Bam. Done. Alright, whoops. Wrong. No, that's my meal plan. What the hell? Alright, so if you look here, this is a velocity time graph, which is a bit harder. Let's label the parts. What we need to understand is acceleration is equal to what? Your velocity, or your change in velocity over time. Now this is very important, right? It's similar. So what we have here is, if you want to know what this represents velocity divided by time, which is there, which means it represents acceleration. If this line is constant, that means acceleration is also constant. So you write constant acceleration. If you guys know all the formulas and apply them to graphs, trust me, it comes so easy. How about here? Your line is flat, which means whatever's here is constant, which is constant velocity. So your speed is the same. Where else do we have constant velocity here as well? Whenever you have flat line. Yeah, I think that's very simple. If you're confused about what the flat line represents, look at what this axis is, and that's just constant wherever's there. So if you go back very quickly, if you look here, flat line was basically you have a constant distance, which just means it's stationary because you're not moving your distance. That's what it means, yeah? So constant velocity here as well. Here we have constant deceleration. You guys might be asking why not acceleration? Is because why? You have a high velocity there, you're going back to 0. So your speed's going back to 0, so you're slowing down. So deceleration is slowing down. And here you can just say non-uniform acceleration. So you are accelerating, you're getting faster, but it's not uniform, it's not like constant, yeah? So there we go. If they give you questions, basically, just let me do one quick one. I wanted to go to like 50 billion minutes for the video, but if they give you just for a straight line like this, so it's a velocity time graph again. They might tell you the velocity there is 50, and then the time at that point is about 8, right? So what we do is, acceleration is what? Change in velocity. So you started at 0, you went to 50, so the change in that is 50. And then you went over, change in time, which is what? From 0 to 8. So you do 50 divided by 8, which I believe is 6.25 meters per second squared. Yeah, one last one again. Again, you have a velocity time graph. They might tell you there's 12 seconds. The highest point there is 60. All we do is what? You're changing a velocity, which is 60, divided by your change in time, which is 12. And that gives you 5 meters per second squared for your acceleration. Yes, you have to understand and kind of get this formula there. All right.